While an airplane is in flight, there are four forces acting upon it. They are lift, weight, thrust, and drag. Lift is the upward force created by the wings as air flows around them and keeps the airplane in the air. Weight is the downward force toward the center of the Earth, opposite lift, which exists due to gravity. Next, we have thrust. This is the forward force, generally created by the aircraft's propellers or turbine engines, which pulls or pushes the aircraft through the air. Finally, there is drag. Drag is the force, acting in the direction opposite of thrust, which fundamentally limits the performance of the airplane. When an aircraft is maintaining its heading, altitude, and airspeed, it is said to be in straight and level, unaccelerated flight. In unaccelerated flight, lift equals weight and thrust equals drag. Let's look at these four forces in a little more detail. The key to an aircraft being able to fly is lift. Looking at a cross-section of a wing, we can better understand how the lift gets generated. A wing is a type of airfoil. Airfoils, in general, are just any surface that generates an aerodynamic force as a fluid. In our case, air moves around it. Don't confuse a fluid with a liquid. Fluids are any substance that deform under an applied stress. Liquids, gases, and plasmas are all considered fluids. In addition to the wings, all the flight control surfaces, as well as the propeller, are considered airfoils. The aircraft's fuselage is even an airfoil, but it's not very good at producing lift. Before we get too in-depth, let's introduce a few new terms. The forwardmost point of the wing is called the leading edge. The aftmost point is called the trailing edge. If we connect these two edges together with an imaginary line, this line is called the chord line. As an airplane flies through the air, the path that the plane travels along is known as its flight path. The airflow that flows around the airplane as it travels through the air is known as the relative wind. The relative wind is parallel to, but opposite, the aircraft's flight path. The angle between the wing's chord line and the aircraft's relative wind is called the aircraft's angle of attack. The angle of attack is a major factor as to how much lift the wings generate. So now that we've got those terms out of the way, how does a wing actually create lift? Well, there are two major theories working in unison that explain the creation of lift. These are Newton's three laws of motion and Bernoulli's principle. While all three laws of motion apply to flight, the third law has the most significance to lift production. Newton's third law states that for every action, there is an equal and opposite reaction. If you stick your hand out of a moving car's window, you will notice that your hand will want to lift up. By rotating your hand, you are deflecting the air that comes in contact with your hand downward, and as a result, the air will push your hand up. This is similar to how a wing works. In normal flight, as air flows around the wing, the air gets deflected downward as it flows smoothly around it, and as a result, the wind will lift the wing up. The other main theory of lift is Bernoulli's principle. The principle states, as the velocity of a fluid, in this case air, increases, its internal pressure decreases. We can visualize this by having air flow through a tube with a narrower middle section, which we call a venturi. As air enters the tube, it is traveling at a known velocity and pressure. When it arrives at the narrower portion, the velocity increases to allow the air through. As the air's velocity increases, the air's pressure decreases. Then, as the air exits the narrower portion, it returns back to its original velocity and pressure. Now, let's flatten the top part of the tube. Granted, the effect will not be as pronounced, but there will still be a change in velocity and pressure as the air moves through. Now, how does this relate to a wing? Well, if we replace the bottom protrusion of the tube with a wing, in essence, we have the same thing as a venturi. As the air passes over the wing, each layer of air gets deflected less and less until finally we reach a layer where the air is not disturbed at all from the wing. This can be thought of as the top of the venturi. An airplane's wing is shaped similar to that of a venturi. The top is rounded while the bottom is relatively flat. Because of this, the air traveling over the wing will increase in speed, and as a result, will have a lower pressure than the air below the wing. This imbalance in pressure is called a pressure gradient. Wings are designed to create this kind of pressure gradient because air always moves from areas of high pressure to areas of low pressure. Since the wing is stuck in between the two areas of unequal pressure, it is lifted towards the area of low pressure by the force of the higher pressure air trying to move to the low pressure side of the wing. Now that we've covered the two theories behind lift, let's discuss all the factors that determine how much lift is produced. The best way to discuss this is through the lift equation. Don't worry though, this isn't a math lesson. Lift equals 1/2 times the air density times the surface area of the wing times the airplane's velocity squared times the coefficient of lift. For the most part, this should be fairly straightforward. The only one that might confuse you is coefficient of lift. The coefficient of lift is simply just a number that is associated with a particular shape of an airfoil, as well as the airfoil's angle of attack. Generally speaking, there are really only two ways a pilot can control the amount of lift the wings can generate: airspeed or angle of attack. The faster the airplane travels, the more lift the wings will generate. Similarly, the higher the airplane's angle of attack, the more lift the wings will generate. However, there's a limit to this angle. Let's look at this using a chart. The chart is plotting the coefficient of lift of a particular wing as its angle of attack increases. Lift will continue to increase until a certain angle of attack, called the critical angle of attack. After this point, the wings will still create lift, but the amount of lift created is decreased. This is called a stall. More information on stalls will be covered in a future lesson. In addition to the aircraft's airspeed and angle of attack, there are other factors that affect the amount of lift created by the wings. However, the pilot does not have control over these factors. These factors have to do with the design of the wing itself and consist of the wing's planform, camber, aspect ratio, and wing area. The wing's planform refers to the shape of the wing when viewed from above. The camber is the curvature of the wing. A wing with zero camber would be considered symmetrical about the chord line. Camber is usually designed into an airfoil to increase the maximum coefficient of lift, and thereby minimizing the stall speed of the aircraft. The wing's aspect ratio is the relationship between the length and width of the wing. Generally, the higher the aspect ratio, the more efficient the generation of lift is. For example, gliders have really long, skinny wings, giving them a higher aspect ratio compared to a Cessna 172. Finally, there is the wing area, which is simply the total surface area of the wings. The larger the wing area, the more lift the wing can produce. Looking back at the lift equation, we can see that the wing area is incorporated into the equation. The rest of the wing shape factors are merged into the coefficient of lift variable. We saw how pilots can control the lift generated by the wings by changing the aircraft's airspeed and angle of attack. However, most airplanes come equipped with one or more additional ways for the pilot to manipulate the wings and, in essence, change the shape of the wings. These are called high-lift devices, the most common of which are trailing edge flaps, or just flaps for short. High-lift devices, such as flaps, are designed to increase the lift and drag generated by the wings at low air speeds. Flaps are particularly important for the approach and landing phases of flight. Use of flaps during a landing allows the pilot to fly at a fairly steep descent angle without gaining airspeed, and allows the airplane to touch down at a much slower airspeed. Flaps can generally be lowered in steps, or more precisely, in set degree amounts. Initially, the input of flaps will increase lift by a larger amount with only a small increase in drag. As the flaps are extended further, usually around the halfway point, lift increases only slightly, and the amount of drag created increases rapidly. Now that we have an idea on how lift is generated, let's discuss the three remaining forces, starting with weight. Weight is the force of gravity pulling the aircraft back down to the earth. This force always acts vertically downward to the center of the Earth, no matter what the aircraft's attitude. The weight force always extends and pivots from the center of gravity, also known as its CG. Keep in mind that the weight of an aircraft is not constant. It will vary with the equipment that is installed, as well as the passengers, cargo, and fuel. Throughout the flight, the weight will slowly be decreasing as fuel is burned to power the engine. Next is thrust. Thrust is the forward-acting force opposing drag, which propels the airplane through the air. In most general aviation airplanes, thrust is generated from the propeller. Larger jets get their thrust from their turbine engines. Similar to lift, thrust is generated from the same principles as lift, but in a horizontal direction. A propeller is an airfoil. As such, as it rotates, its blades accelerate the surrounding air towards the aft end of the aircraft. And as illustrated with Newton's third law, the equal and opposite reaction results in the aircraft moving forward. And finally, we reach our last force, drag. Drag is the force opposing thrust, which limits the forward speed of an aircraft. There are two types of drag, parasite and induced drag. Parasite drag is a direct result of the air resistance as the airplane flies through the air. There are three types of parasite drag: form drag, interference drag, and skin friction drag. To learn about these three types, check out the bonus video on parasite drag. The amount of parasite drag varies with the speed of the aircraft. As the airplane's speed increases, the amount of parasite drag will increase. In fact, the amount of parasite drag you experience is directly proportional to the square of the airspeed. For example, an aircraft traveling at 120 knots will experience 4 times as much parasite drag as the same plane going 60 knots at the same altitude. The other kind of drag is lift-induced drag, more commonly called induced drag. While the wing is creating lift, behind the wing is a downwash of air. At the same time, the airflow around the wingtips are creating vortices that spiral from below the wing to above the wing. As these vortices wrap around the wing, they actually change the downwash angle of the air flowing over the wing. This, in effect, tilts the direction of the lift created backwards. This shift from completely vertical lift to slightly aft lift is due to induced drag. Induced drag is higher at slower airspeeds and decreases as we increase speed. This is because induced drag is worse when the airplane is flying at a high angle of attack, like when we are flying slowly. One way that a pilot can experience reduced induced drag is by flying in ground effect. When flying within a wingspan of the ground itself changes the downwash of the air flowing over the wings. This shifts the lift vector forward and reduces the amount of induced drag. Pilots can take advantage of ground effect when performing a soft field takeoff. This lets the airplane lift off the ground before the regular liftoff speed. However, they'll need to hover over the ground for a few seconds to increase their speed before they can continue to climb out. If we take both induced and parasite drag, plot them on a graph, and add them together, we get a new curve representing total drag. The lowest point on the total drag curve shows the airspeed at which we make the most amount of lift and the least amount of drag. This value is called L over D max, or as pilots know it, our best glide speed. Pilots should be familiar with this number, because in the unlikely event of an engine failure, this is the speed at which they'll want to glide down to the ground. In a no-wind condition, this speed will give the pilot the best glide ratio, meaning that they'll be able to stay aloft the longest to maneuver to their intended field for emergency landing. Note on the left side of the total drag curve, the slower you fly, the more drag you create. In this region of airspeeds, sometimes called the backside of the power curve, the pilot will actually have to add more and more thrust to counter the high amounts of drag being created. In fact, if they want to accelerate out of this range of airspeed, they will have to add an excessive amount of power, maybe even full power. One other thing to keep in mind at slow airspeeds is that there is much less airflow traveling over the flight control surfaces. As such, Any input you make on the flight controls will not have the fast response one would be used to. The flight controls will feel mushy, and they may require large inputs before any real response is felt. While the finer details of the principles of flight can seem a bit overwhelming at first, gaining a basic knowledge of how the airplane flies provides the pilot full understanding of all the forces at work and the best methods and techniques for controlling their aircraft. A good pilot doesn't just drive their plane from point A to B, but instead understands the art and science of how their plane flies.